Welcome back to Introduction to Artificial Intelligence. Thanks so much to all of you who are coming back. Just before we jump in, I just wanted to highlight some resources if anyone is interested. So first of all, I really want to plug the great work that John Halverson and his team does in research computing, putting together so many opportunities throughout the year for all members of the Princeton community to come and learn about topics such as this, as well as a wide variety of other topics pertaining to research computing. So please, make sure to check out those offerings. In case this wasn't enough of me, I do offer 2 semester-long courses, one at the grad and one at the undergrad level. They share a lecture and cover much of the same content. And so if you're a student, you'd be most welcome to take it. And even if you're not a student, if you're a member of the Princeton community, I certainly welcome auditors. You could just reach out to me. Teaching it right now and teaching those classes also, I expect in spring of next year too. Just in case anyone is interested in learning Python coding, so I have a pretty minimal Python crash course. It's directed at complete beginners. It doesn't cover all aspects of the language, but it does cover the sort of fundamentals that you need to jump in and start doing some stuff with code. So if you have a PUID, then you can go ahead and sign up for that if it's of interest to you. So just to recap what we said last time. By the way, we'll share these slides afterwards. I gave my slides to John from yesterday, and I'll share these ones also, so you can have those links in a more clickable format. Oh, here, if people here, I'll pause for a minute. Why don't people come and actually take seats, because there are a number of empty seats. I don't mind. Don't be shy. You don't have to sit on the floor. Unless you really want to sit on the floor. You always feel bad. Students in my class will come and sit on the floor, even though there's like empty seats in the middle, but the students always sit on the edges. They don't want to push past them. Yeah. So there's 2 seats here if you want. Okay, so as you'll recall from yesterday, one of the first things that we did together was train a model from scratch to recognize handwritten digits, right? And I showed you how the model, when I first created it, was populated with random weights and biases. So it was still able to make predictions, if we want to call it that. Guesses probably is a better word, about which category, which number a given handwritten digit corresponded to. And then I trained it by letting it see 60,000 training examples. And it took about probably 30 seconds on my laptop, right? And after that, it was able to attain 98% accuracy. And what we walked through last time in some detail is exactly how, given a set of weights and biases, it's able to take an input, that is a picture, and if you remember, we unrolled the picture. Picture to a computer is a square of numbers, or a rectangle of numbers, I should say. And we unrolled this into one very long list by just taking the first row, and then the second row, and the third, and so on, and so forth. It was 28 by 28 image, and so since 28 times 28 is 784, the inputs were always 784 numbers. And what we saw last time is what we then did was compute 512 weighted sums of these 784 numbers. So there were associated to this hidden layer 784 times 512 weights. This is approximately a little over 400,000. Okay, here this would be one weighted sum. A weighted sum of all of these 784 pixels. Here would be another weighted sum, another one, and so on. And to each of these, just to give ourselves a little more flexibility, we also added a bias term, quote unquote, which is just a number that we added to the sum that was independent of the input. So a number that didn't weight anything, but just simply added to the number. We then applied a nonlinear function, just really anything that takes you out of straight line land, right? Anything at all that isn't multiplication and addition would potentially serve here. We chose to use a somewhat funny function, ReLU. So if here's my straight line, ReLU turns it into something like this, where it leaves positive numbers unchanged, but flattens out all of the negative numbers to 0. And we saw how this allowed our function in a really concrete, very simple but very concrete case to learn to separate berries such that small and purple and big and pink or something like that were poisonous, and the other two possibilities were safe. Something that drawing a straight line, a linear model, was not able to do. Simply adding this ReLU function in there let us use something bendable to separate out our categories, right? That's the importance of this ReLU function in this hidden layer. And indeed, using ReLU here for the handwritten digits, since that is a much more complicated space than the berries case, as Professor Bjorkman correctly pointed out. We could actually easily write down a rule that would have separated the berries there, right? It's a sort of toy example. Really unclear if it's at all possible to write down any kind of strict rule here that would, on the basis of pixel values, give you good categorizations as a 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Certainly we as humans do not know how to write down such a rule, right? But this model such as this, especially once we allow it to learn nonlinear curved functions, is able to do it, okay? So those are these 512 values in the hidden layer. And then what we did was we then computed for the output another 10 weighted sums. This time what we're weighting are these 512 values from the hidden layer. And we again allow ourselves 10 bias terms just to give a little more flexibility. This gave us 10 numbers, and at this point the machine was doing well if it gave big positive numbers to the correct category and small negative numbers, large magnitude but negative numbers for categories to which the number didn't belong. But this is kind of hard to interpret. It's hard to train the model without this. So what we decided to do was transform this into a probability distribution over these 10 categories by applying a function called softmax. And really the important takeaways about softmax is that if you have one very large positive number, softmax is going to translate that to something very close to 1. If the other ones are negative numbers, those are going to be translated to probabilities quite close to 0. So it'll give us something that ideally, after we've trained the model correctly, we'll assign a high probability to being a 9, let's say, if the input is indeed a 9. Okay? So this is the forward pass of the neural net. This is how it takes, given a set of weights and biases, takes you from an input to a prediction. As we saw, that prediction could be really good or could be really bad, right? It was really bad before we trained it. It was at about 10% correct because it was literally choosing 10 out of 10 possibilities at random. And then by the end, it was 98% correct. And probably with this data set, I'm not even sure a human could do much better than that, since some people just have terrible handwriting, and it's really hard to tell what the digit was supposed to be, okay? So that's how, if you have a set of weights and biases, you get a prediction. But how did we get from these random predictions, these random weights and biases, to something that did like pretty close to human level performance? How did we go about doing that? What happened in those 30 seconds when my laptop trained the model? So to put this differently, right, here's a sort of simpler, smaller neural net, but they all work the same way. Really, where do these weights and biases come from? Okay, so maybe this is like a simple model, like predicting a house price or something like that. Where do these weights and biases come from? They start randomly. I'm telling you that. What happens after that random initialization? Okay. So here's a conceptual overview of gradient descent, which is a sort of algorithm or species of algorithm that turns out to be absolutely crucial. It's at the heart of training all modern AI systems. As they say, it's going to be randomly initialized. You just have to start somewhere. You can't start nowhere. You have to start somewhere, right? Terrible predictions at first, that's fine. Then what's going to happen is that for each and every one of these weights and biases in the model, the machine is then, this is just gaining some intuition, is going to ask, okay, using this set of weights and biases that I have, I ran it forward and I made a prediction. I predicted that that was, let's say, a 7. And then remember that what I gave the model wasn't just inputs, but also correct answers. All of my digits were labeled, so the machine could then say, okay, I thought this was maybe a 7. Let's take a look. Oh, in fact, it's a 9. How could I change each and every one of my weights and biases, in this case 400,000 plus of them, how could I change each and every one of them just a little bit so that my prediction next time will be better? Goes forward, makes the prediction, looks at the answer, and then walks its way back through the model asking what changes will lead to a better prediction next time. Okay? So that's the sort of high-level roadmap. Right? And it's going to actually make the adjustment in that direction. So so how does it actually implement this? So here is, so just to gain some kind of intuition here, so these are like, I know, funny AI-generated images from a few years ago. I should probably update them. So just to kind of, just forgetting about machine learning for a minute. So suppose that you are out hiking in the mountains, okay? You've camped at base, like the lowest point in the valley, and you go out hiking up the mountains, having a great time. Then all of a sudden, a very, very thick fog descends on the mountain. It's so thick that you can't see where you're going. You can't see which direction it goes, leads you down the mountain, right? You just can't see any of that. What do? And then suppose you have the following thought. Well, look, I know that I have to get down the mountain. If I get down the mountain, I'm in good shape. I can't see which direction is down, but I can feel the ground underneath my feet. I can feel around, and I can feel which direction points in the direction of steepest descent. Okay, which direction does the ground slope down the way the most? I take a little step in that direction. Then I repeat the process, feeling around under my feet. Take a little step in the direction of steepest descent again. Feel around, repeat the process. It may not be the best way down the mountain, but that's a way of generally getting down the mountain, right? Maybe it doesn't get you exactly to your camp, but metaphors are not perfect. It at least is a way of descending the mountain without having any kind of broad overview of where you're going, just simply relying on this very local information that you can, in this case, feel through your feet, okay? What if we could leverage something like this mathematically? This process of gradient descent, taking little steps in the direction of steepest descent, turns out to be a highly effective way of finding the minima or lowest points of a function. So can we find a function, something mathematical is all that means, that is minimized, that hits its lowest point when our predictions are as good as they can be? Then maybe we could use information about the slope of that function to take little steps down it in the direction of steepest descent. Okay? So let's walk through this. Let's focus on the case of predicting quantities like house prices rather than classification. Okay, I'll come back to classification, but so not handwritten digits, right? Not berries safe or poisonous, but things like how much does this house cost? Something where where the answer is a number. Okay. So it's something like we probably want to minimize the difference between our prediction and the correct value, right? If I have a house that's sold for, let's say, $500,000, then I want my prediction, ideally, to be pretty close to 500,000. I don't want there to be a big difference between my prediction and 500,000, right? This is pretty obvious stuff, okay? Here's one thought that we might have that's not a very good thought, is maybe we take the prediction and then we subtract the correct value from our prediction. So we just take whatever I predict and subtract the correct answer. I'm going to call it 5. Think of that as standing in for, say, 500,000, something like that. I'm just going to, say 5, all right? Well, the problem is that this gives us a function that can always be made smaller, right? This function can always be minimized. This would be like a terrible mountain to be descending, because you would descend and descend and descend forever, right? It doesn't actually have a minimum. And what's more, if we thought that what we needed to do was minimize this function, it would suggest that we would be creating ever better predictions by predicting that the house sold for negative 500,000. No, wait, negative 700,000. No, wait, negative 5 million, right? These are better and better predictions. Of course, they're obviously not, right? This is a terrible function to use. Let's try something else, right? So we could try taking the absolute value. That's a much better idea. And you could train a model with this function, right? So here's the absolute value, right? I just replace the negative numbers with the corresponding positive numbers, right? We could totally work with this function. It just turns out that actually computationally, this is a little bit of an ugly function to work with. A little bit intuitively, if you were imagining skiing down a slope, this would be a kind of nasty function to ski down, because you go faster and then crash at the bottom, right? It's just a little bit undesirable like that. So what I'm going to do is I'm just going to essentially take this function, but give you a smoother, more curved version of it. I'm going to do this by squaring the difference, right? So squared numbers are always positive, right? Take a negative number times itself. That's going to give me a positive number, so I don't have this like shooting off to negative infinity problem. But now I have a nice, smooth, curved function. Mean squared error, this is sometimes called. Okay? I can just compute this by taking the prediction that I made, subtracting off what the actual value is, let's say 500,000 in this case, squaring it. And then, in fact, I'm going to also multiply it by a half for reasons that really, I wouldn't worry too much about it. We're not going to get into derivatives here, but at some point I'm going to take the derivative of this. And if you remember calculus, this 2 will come down, and if I have a 1/2 there, it'll go away, and I don't have to worry about it. If that doesn't register with you, that's totally fine. Just don't really worry about the 1/2, but it's there. And this is kind of a nice function now. We could like sort of roll a ball sort of nicely down the function, right? Kind of nice function to work with. Wouldn't be so bad to ski down this function, right? This is a nice function to descend, okay? A function that takes as input our predicted value and the actual value, the correct value, which comes from the data set, and computes on the basis of that something that if we minimize it, we're making a perfectly correct prediction. So if all I needed to tune was somehow directly my prediction and I knew the correct answer, I could do that pretty easily, right? But in fact, what I need to be able to do is compute the prediction from the input, right? A prediction isn't something that the machine learns. What the machine learns is good values for the weights and biases that take an input, right? I mean, just tuning the prediction directly is almost like just memorizing that, say, the answers to a true or false test, or like true, false, false, true, false, right? That might work for that test, but it works very, very badly for other tests, right? You need to have something more robust that is input dependent. We need to be able to compute our predictions from the weights and biases. They're the things we need to tune, okay? So let's kind of blow this up. So suppose I'm literally computing for an actual house. Okay, suppose here's an actual house. Suppose I made some observations about it and I compute a prediction for this actual house. And suppose my model, as it stands, predicted that this house would sell for, let's say, 8, suppose that's in 100,000, like 800,000 is the prediction. But suppose instead, when I actually look at the housing records, let's say this house instead sold for 500,000. Okay? So that's where my prediction is. That's where my prediction would, where I'd like my prediction to be, right? And you can see again, if I descend successfully on this function, then my prediction will end up in a really good place. So what I want to do, the sort of equivalent of feeling the slope beneath my feet if I'm climbing a mountain, is to compute the slope of this function at this particular point. Okay? So all I mean is I'm just going to take a straight line that just kind of kisses the function at exactly that point and doesn't, doesn't sort of otherwise cross it, at least not in that vicinity. And I just want to compute the slope of this line, the rise over run, right? Just pretty basic, basic algebra. It turns out if you use a little bit of calculus and compute this, right, you actually turn out to have a slope of 3 at this point, okay? That just means that for every little step I take in the x direction, I go 3 times that little step upwards in the y direction. That's all that that means there, okay? So that's the slope of the loss function. This is the loss function, what we're sort of losing as far as our predictions go. That's the slope of the loss function as a function of the predicted price. Okay? So let's just kind of put a pin in that and remember that. And now let's think about the predicted price as a function of the various factors we're considering here. Okay? What I'm going to show you here is like the absolute maximally simplest model. This doesn't even really count as like machine learning model. It's a linear regression in one variable, but if you get the intuition on this, you have the intuition for the rest of it. So let's say that this house, this concrete house I'm considering, right? So let's say that I am at some or other point in training. Maybe this is randomly initialized. Maybe I've been training for a while. It doesn't matter. The process is the same. Suppose that it so happens, right, so my prediction, this is just a linear model. I'm going to compute it as some weight times the square footage of the house plus a bias term, right? Something that just doesn't constrain me to have a price of 0 if there's 0 square footage. I don't know, maybe the lot itself is worth something even if there's no house there, right? It gives me that kind of flexibility. Okay, so these are just random numbers that I picked, that maybe this W, this weight is 1.9 and this B is 1.35. Like, honestly, I picked these numbers at random, so you could think about this as a random starting point. So this is the kind of usual way that we're used to visualizing data like this, I think, right? We're thinking of, okay, the square feet is the thing that's the input, and then it's given some kind of weight, and then maybe there's something that means I don't have to cross at 0, 0, okay? So I can think about my prediction as a function of square footage. This is probably like the most natural way of thinking about a prediction here. The square footage is the input, comes from the house itself, and then the model maps that square footage to a predicted price. And of course, ideally, you would consider more than square footage, but let's just keep this, nice and simple and easy to graph, right? And for this house, let's suppose that its square footage is in fact 3.5 thousand square footage, right? I don't like dealing with thousands, that's why I'm just truncating everything. So it turns out it's like right here, it's somewhere around here, and that's going to be 8, which is indeed what I predicted for this house, okay? So my prediction, right, which was 8, which we saw on the previous slide, is just this weight 1.9 times the actual square footage, 3.5, plus this bias term, 1.35, okay? Hopefully this is, straightforward to the point of maybe being a little boring. Here's what I want you to notice here. So we have here, the prediction is a function, I'm writing it here as a function of square footage, But actually, if we just look at the math here, here's one quantity times another quantity plus a third quantity. I can just as well think of this, once I fix on the house with a particular amount of square footage, I can just as easily consider the prediction to be a function of this weight W. Or indeed of the bias B, but I'm just going to focus on the weight W, okay? It's just two numbers multiplying each other. I can consider one to be the variable, like the square foot, and the other to be the slope. Or I can turn it around and consider the other one, the square footage for this house. It's this specific house I'm considering. Here is how the predicted price for this house varies as I change my W value, okay? So I'm just changing how I'm writing, what I'm writing as a function of what. Totally legit to do it this way. So now my prediction is not a function of square footage, but a function for this house of the weight that I attach to the square footage. Square footage here is 3.5. That's now the slope of this line, right? Because it's the thing multiplying the variable, like y equals mx plus b. Here's our b, right? And now this m, the slope, is 3.5 here. The prediction remains 8 there. And so I actually know here, just from that, right, it's a line. I just compute mx plus b. A tiny little change in this direction here is going to produce 3.5 times that change in this direction here, okay? And now, what I graphed here, I kind of put these two functions together. Now I'm showing you, it looks similar to before, it's the loss, but it's not loss as a function of prediction anymore. It's loss as a function of W. Considering this particular house and keeping the B value, in this case, unchanged, okay? Keeping everything else the same. I'm looking at the loss as a function of this weight W. Because really, this weight W is the thing that I want to change. This is really the mountain that I want to descend. Okay, everything else was a kind of intermediate step along the way. This is the thing, because W is the thing I can change. So what I just want to do is change W in a way that takes me down this mountain, right? And it's super obvious when you look at it like this, but let's just walk through the discipline of putting this together. What I really want to know is the slope of this, the loss, as a function of W, okay? It turns out if I know what the change of the loss is with respect to prediction, which we computed before, it turned out to be 3. And I know what the change in the prediction is with respect to W, which we computed a moment ago. It's just the particular square footage, 3.5. In order to put these together, all I do is multiply them together. The change in loss with respect to W is just the change in loss with respect to prediction times the change in prediction with respect to W turns out to be 10.5. It's the chain rule from calculus, but it's also kind of common sense. You've got these two things. You change the one, you produce a 3.5 change in the one, which itself produces a 3 times that change in the other. What do? I don't add them, I multiply them, right? It's just kind of, what else would you do, right? The chain rule from calculus. And I'll just point out that in keeping B fixed here, we're essentially actually taking, what we're actually really doing is taking partial derivatives here. If you call it that, it sounds like something very complicated. This is all actually that really comes to, okay? So now I actually have a number for the slope of this function as a function of W. And what I'm going to do is use that, and I'm just writing this here, this d loss dw. That's just a compact way of writing the change in the loss with respect to W. It's just a compact way of writing it. And down here, this would be the change in the loss with respect to B, the y-intercept. I didn't walk through that, but it's very much the same kind of computation. It's in fact slightly easier. And what I'm going to do is I'm going to use these numbers, these slopes, to change my values of W and B, right? So I don't just feel for the slope under my feet, I actually use that slope to take a step in the direction that brings me down the mountain, okay? And so what I'm going to do is take my old W value, and I'm going to subtract off this number, this 10.5 that I just computed. But I'm actually just going to do something which is multiply it first by a very small number called a learning rate. Just turns out, and then if you think back to the mountain analogy, if I feel, suppose the ground's very uneven under my feet, but I feel around and I take like a big step, maybe I end up going up the mountain. Like I could sort of overstep that. You're only confident in this little local region, so you just want to take a little step. That's all alpha is really doing here, just keeping you from taking overly large steps that might end up being counterproductive, okay? And it turns out in this particular case, if I go through actually literally this computation, here I computed d loss dB, the change in the loss with respect to B, which is 3 here. It turns out I get these new values, updated values for W and B. And then if I go back to this house, my predictions for the cost of this house, and plug them in, I'm now predicting 7.92, whereas I previously predicted 8. And my loss, my sort of metric on how badly I'm doing, has gone down from 4.26 to 4.26 from 4.5, so I'm doing a bit better. This might seem excessively laborious for a particular example, but we're just walking through step by step how we might implement this in the simplest possible case. Where this really kind of shines is obviously going to be a much more complicated example, like where my laptop computed yesterday. The derivatives, the gradients, the slopes for each and every one of, I think it was 407 plus thousand parameters all at once, and it asked for each and every one of these using just exactly the computation I just showed you here. What direction, what little change, and sort of what the magnitude would be that would lead those weights and biases each individually to contribute to a better prediction next time. It turns out if we can do this for 1 W, we can do it for 400,000 Ws, or we can do it for 3.3 million Ws, or indeed in the case of LLMs for billions of Ws and Bs all at once. Of course, as humans, you don't want to be in the business of literally computing this, but computers are like, great, I gotcha. It's very simple, very mechanical process. This is called the backpropagation algorithm, or at least it would be once we sort of push it through multiple layers. This is what is used to train all modern AI applications. It is just simply making predictions and then asking for each of those predictions how, via this exact calculation, how we might change those values so as to make a better prediction next time. If we graph it, we can see we've indeed successfully a little bit descended our loss function for this particular example. So let me show you just kind of like maybe another visualization on it. We're still in linear land. The problem is once we get to more complicated, I will actually show you a more complicated visualization later, but the more realistic it becomes, the higher the dimensionality and the less sort of visually obvious it is. So suppose that I've gone through the process of collecting the square footage of a bunch of houses that have recently sold, and I've also collected data on their price. In fact, this is just like synthetic data that I generated, but we can pretend that I actually collected the data. And I'm going to start by picking some random values of W and B. Again, I'm just going to use just a linear model here just for intuition, right? Some W, some B. My prediction is W times the square footage plus B, okay? Now, let me just kind of show you what happens if I just start picking points and making adjustments based on those. So let's pick a particular data point, an actual house, let's say. Here's what the house actually sold for with its square footage, and here's what my model's predicting it sold for, okay? That corresponds to the loss, that difference between the two. Pretty big loss here. I'm pretty far off. It's not a great prediction. No surprises. These were random numbers, right? And then it turns out if I go through the computation that I just showed you, I get these values for the change in W, and this value for the change. Oh, that should actually be a B there. I apologize. That number for B. I just do the same calculations I showed you before. I just already did them. And so I make little adjustments now actually to W and B, which are going to change the slope of my line. Okay, so here it was before, W and B. These guys will change when I click. See, now they both changed. And it got better, right? It improved the prediction. Now let's pick another data point. And this one I'm doing much better on. I'm still going to go through the same process, take a little step towards being better at it. This produces less of a change, right? I was less far off, so my change is less dramatic. Pick another one, come down just a little bit here. Here, this is kind of big, so I'm going to have a bigger jump. Here's one that's above it, so I come up a bit towards that. So we could keep going like this. Taking it one training example at a time like this, it's going to be a bit slow, and I'm going to get some amount of oscillation. Okay, so can I do a little bit better with my training? So conceptually, what I say to my students is if you understand how to do this for a single training example, that's the main thing. The main thing is just understanding conceptually how we exploit the information in one training example to update the weights and the biases for the model. Conceptually, that's the hurdle, right? That's the thing to focus on. But practically speaking, what turns out to be better is actually to consider a whole bunch, or maybe I should say a whole batch of training examples all at once. And then what I want to do is compute those gradients for all of them, compute for each individual one what the direction and magnitude of the steepest descent in the direction of each weight and bias is. But then I'm going to take the average of those. Now I'm going to be less pulled around by, say, outlier data points. You can imagine in a house price data set, maybe like a house seller had some personal reasons for wanting to sell their house very quickly, and so they took a much lower price on it, for example, right? All sorts of outliers. Averaging just kind of smooths us out, right? If you think about kind of coming down the mountain, taking a step each data point at a time is like a very sort of like random process, right? When I smooth that out, I'm going to kind of descend more straightforwardly, all right? And in fact, if you looked at the code that I wrote for the handwritten digits, you would have seen something where I said batch size equals, and I said 128. So that actually meant that I was asking my computer to consider 128 of those 60,000 examples all at once, and compute the gradients for each one, just according to this process, just this pretty basic calculus process, but then average those gradients and use those averages to take the little steps, okay? So that's what it did, right? It takes a gradient step based on the average. Having made that update, it then moved to the next 128 examples and so on until it had gone through every example in the training set. That's called an epoch, one epoch of training, okay? And then it started over again at the beginning. I'll show you more of a visualization of this in a moment. Started over again at the beginning and repeated the whole process. And it did that for as many times as I told it to. And in that particular case, it turned out I told it to do it 5 times. Why? Because it wasn't my first time doing it, and I knew that 5 would be enough to get us excellent accuracy. And actually going back to a question that we had last time, in some cases, if I trained it for many more epochs than that, I might actually get lower performance because it starts to pick up on very specific features of the input data set. So there's some art to choosing the number of epochs. So let's see if we just really, to make it concrete with the handwritten digit data set, Suppose I'm at the beginning of my first epoch. I have 60,000 training examples total. That's what I had. And I specified a batch size of 128. So it turns out the 128 goes into 60,468 times with a remainder of 96. So I took that first 128 examples. That was my first batch. Took all of those, and in parallel, all at once, my laptop made its very bad, very random predictions for those 128 examples, right? It walked it forward, ran it forward, and then for each of them it looked, okay, this was in fact a 9, this was in fact a 7, this was in fact a 0, right? All 128 of them. And then it said, okay, how could I adjust each and every one of my 400 plus thousand weights and biases such that I would make better predictions next time? For each of those, it calculated that, then averaged those gradients, then walked back, as it were, and actually made those adjustments to those weights and biases, okay? Right, so we start with initial random weights and biases, go through that process, make the predictions, compare each to the true label, compute those gradients and average them, and then use those to take a gradient step. And now, what I have are updated weights and biases. Each of these 400,000 plus weights and biases are now a little bit better, because now they've seen some data. Now they're not totally random. And so what I do, the machine does, I should say, takes the next 128 examples in the data set, and using those current weights and biases, walks forward with them, makes the predictions, and then sees how well it did on those predictions. Then asks again for each of those 128, how could I do better? Takes gradient steps on those weights and biases for each on the average of that 128. Okay, and then we move forward to the next batch and with our updated weights and biases, and so on for whatever it is, 468 batches, I guess 469 batches, I suppose. We get to the last one, right? Make our prediction. This is a small batch. We only got, I guess, 96 examples in it. Doesn't matter. Run those forward, make our predictions, right? And come back, make our adjustments, right? And now we have come to the end of our first epoch of training. At this point, we have seen and made adjustments based on every single example in that 60,000 training set. Okay. And it was kind of, I don't know if you remember, but my laptop was sort of showing like a little each of those was epochs, actually. And it did it 5 times because I told it to do that, right? So it then came over with its weights and biases from that first epoch and embarked on the next epoch, following exactly the same, really very mechanical steps. And once it had done 5 full passes through the training set, those weights and biases had been adjusted so well by that point that we were able to make predictions on this data set with 98% accuracy. There was absolutely nothing else that went on. There was nothing I'm holding back, no sort of tricks, nothing swept under the rug, no oversimplifications. That was exactly what my computer was doing yesterday. The wonderful thing is that it works. Yeah?
Maybe I missed this, but am I right to say that because it goes from like one batch, then it sort of does an iteration step, then it goes to the next one. You might say, well, have 5 steps, or some more at least, you know, more than just one, or am I thinking about that wrong?
Wait, I'm sorry, say
Because then it's almost like it's taking the gradient and then it's sort of like doing one improvement, but it might be okay doing that batch, calculating it again, and using that batch again to...
Oh, I see, so like why not take the first 128, make steps that improve it, and then take that 128 again? Is that the idea? Yeah, I mean, you could do it that way. The problem is you're probably going to pretty quickly overfit to that 128 examples. And then when you eventually move on to your next 128, then like you're going to probably have to do a lot of retraining. And what I would honestly worry the most about is whatever final, I mean, in this case, 96 training examples are in that final batch. What you might end up with is a model that is exquisitely well trained to do well on those 96 examples, a model that doesn't generalize all that well. It could end up effectively reducing, as it were, the size of your data set. Like trying to train a handwritten digit model on 96 examples is going to be terrible. You don't want to be optimized for only 96 examples. You need more signal than that. Why? Because there's more diversity in handwritten digits, right? So I think those are the sorts of effects that I would be concerned to see, and why you wouldn't want to set it up that way. But I see the question.
More about whiffing everything than like running towards a goal that you know is at a certain location.
Exactly. Thank you. Yeah.
Is there another question?
Yeah. I think you were first, and then you. Yeah.
So all of the weight and bias, when you try to adjust it, now there are some consideration about the relationship among different weights, right? Or different, right? No, you don't.
Nope. So no, we just consider each one independently, and that's actually if you've ever taken a calculus course with multiple variables, ever done partial derivatives, what they'll sort of say is just treat every other variable in the function as a constant, right? And that fundamentally is this idea that these are independent directions, if you like. That calculus really tells you can consider the slopes in this sort of way. So no, there is actually no consideration like that. We just, except in as much as perhaps that if one weight and if anything depends on anything else, that's going to show up. But to the extent that we're just looking, once we start taking the derivatives, we consider everything else to be a constant. Thank you. Yeah.
Yes, I'm curious what it means for a guess to be wrong or close here, because in the house pricing example, it's off by some number, but here is it that like it's off ordinally, where it guesses 5 when it should be 4, or is it like, is the similarity space different where it's like it guesses 9 when it should be 4 because it looks similar? Yeah.
That's an awesome question, and thank you so much. It's almost like I paid you to ask me that. Yeah, I mean, what you just said is exactly. So something we would not want to do, because it just doesn't make any sense, is suppose you try to carry over this logic and say, okay, I'm going to have it output numbers like with house prices, and then I'm just going to say whatever number is closest to that, maybe that's what the digit is. You're just not going to manage to train a model like that. It doesn't really make any sense, because like suppose, like, if the machine at first predicts that's a 0, do we really need it to go through predicting next that it's a 1 and then a 2 and then a 3 and a 4, right? Why should 9 be harder to reach that, right? You don't, and you're exactly right, that probably more likely would be confusing 9s and 4s, because that's actually sort of data relevant, right? So what do we do about classification? Oh, yeah.
So yeah, can you go back to the previous slide?
Yeah.
I was just wondering if there's any value in varying the size of the batches across epochs, and or varying the order in which examples are presented, whether that would improve training.
People don't tend to do that, is the answer. So in general, you just pick your batch size. So the data is always randomly shuffled. It's really important that it be shuffled, because you don't want, for example, like the last batch to be only 9s and it hasn't seen 1s since the beginning, right? Because then it might become really good at classifying 9s and terrible at classifying it. So it's really important the data be shuffled. You don't typically reshuffle between epochs. I don't think it's incorrect to do it, but I guess it turns out to not be particularly critical there. And also the batch sizes. For a model like this, it's not really going to matter that much. It's going to train perfectly well with that. But that could be potentially, if for a given use case, maybe something that makes a difference, where maybe you start out with bigger batches and then go to smaller batches. In a lot of this territory, there is no right and wrong. You could kind of do all of these things and try them out. There are rules of thumb and things that tend to be sort of, pretty automatic as far as coding goes, versus things that you have to customize more. In this sort of territory, what you really want to do is maximize the performance of your model on examples that it has not seen during training. And if you want to do something creative and it produces those results and they're reliable, then that's great. You didn't ever do anything wrong if that's what you did. So a lot of this stuff is kind of guidelines and starting points, rules of thumb. As I say, this is a very sort of performance-based area. So if it gets you good performance on things not in the training set, then like thumbs up. Yeah.
So I see that the 60,000 we divided by 128. It could have been easily be divided by, like, evenly divided if you had taken some other number. So was there a specific reason the 128 was chosen?
Yeah, because it's a power of 2. It's honestly not really any deeper than that. It doesn't matter if the last batch is smaller, so that's typically not something that you particularly worry about. Just because particularly, I mean, if you were doing the thing of like training on each batch a lot, that might be a big concern. But for this, it's, you know, it's seeing all of the examples. So yeah, I mean, in machine learning, you tend to see a powers that are like 2, 4, 8, 16, 32, 64, 128, 256, 512. Remember that one, right? So we tend to use very often powers of 2 in machine learning. I suspect that it actually at this point has more to do with sort of both rules of thumb and communication to other humans rather than being anything of particularly deep importance to the machine. There are cases in computer science more generally where powers of 2 can be more efficient, just given the way that computers compute. They're you know, fundamentally binary systems. So that's where it comes from. I don't actually think it, for this kind of level of stuff, it's going to make a difference. So I mean, this model would have trained just fine if I'd used a different batch size. If I'd used a very, very small batch size, it might have taken longer to train, and it might not have reached the same level of accuracy. There's some advantage to your batch size not being, like a batch of 1, that's the very sort of like jagged kind of step, right? That's usually not the best idea. At the other extreme, you could take your entire data set and feed that in as one batch. One problem with that is you're more likely to run into memory issues. So, you know, maybe for this one, it's probably not, probably this one I could have done in one batch, at least on some devices I could do that. Other times your data set really just may be so big that you'll run out of memory and things will crash. So you don't want that. But then also there's another, you want to have it, waiting until you've gone the entire way through the data set before you take a gradient step is also not very efficient, because you're sort of doing everything all at once. You're going to have to do that many more times, many more epochs, right? So that's going to, even if you don't run out of memory, it's going to be less efficient and potentially less effective as far as training goes. So there's a kind of sweet spot there. And, you know, but beyond that, there are some cases where a model will train much better with a certain range of batch size, and other cases where it doesn't matter that much, and it's going to be very sort of use case specific like that. Yeah, thank you. Yeah. All right, so on to your question, what about classification, right? So the loss function that I showed you before, squared error, works great when our output is a number, like a house price, but it doesn't really make much sense to try to carry this over to like categorizing handwritten digits, right? And we've already said last time how what we want our output to be is a probability distribution over the handwritten digits. So we'd like to have a loss function that jives with that, okay? Let's just take a moment and think, like, what would we like? What is a well-trained model when it's doing classification? What we really want is a model that assigns a high probability to the correct category, right? This is the input. We want a really high probability as our output for being a 9, right? And probabilities, since they all have to sum to 1, if that's a high probability, that just means the others have to be low, right? There's kind of nowhere else for the mass to distribute, right? So we'd like to train our model to assign very high probability to whatever is the correct category, okay? Another way of looking at this, if you remember, kind of mentioned at the beginning, is a sort of duality between probability and how surprising something is. Like you'd be very surprised if I took my dog for an aardvark. Very surprising, right? Whereas like I took my dog for a walk is like banal, boring, unsurprising. maybe we could put it differently and say that we would like the true label, the true category, to be as unsurprising as possible. We're doing machine learning. It's not a 5-year-old's birthday party. We don't like surprises. We like everything to be maximally boring, maximally unsurprising. We want the true label, the correct answer, to be very unsurprising given the probability that we assign to it. So question, can we give any mathematical meaning to the notion of surprise or surprisal? And it turns out the answer is yes. Here is a function that is actually called surprisal. It's a function of a probability assigned to an outcome. In this case, the correct outcome. Let's just look at this function for a moment, right? So if my probability here's 0, here's 1. If I assign essentially close to 1, probability close to 1 to the correct outcome, I'm not at all surprised, right? If it's the middle of summer in New Jersey and you're very confident that it's hot and humid outside and you walk outside and it's hot and humid, you're like, yep, no surprises here, right? You gave it very, very high probability and you were not surprised. As you give something less and less probability, then it becomes more and more surprising to learn that that's true, right? I'd be fairly say it seemed sunny and clear right now when I walked over here. I'm not super confident it hasn't started raining, but probably hasn't started. It probably hasn't started. So if it hasn't actually started raining, there's really not much surprise there, right? I don't have to give it probability 1. I just think, yeah, it's somewhere around here, like 0.6 maybe, that it hasn't started raining. I'm not very surprised to learn that it has not started raining. So give that point. Suppose that it's like summer in New Jersey. You give it almost 0 probability that it's snowing, and you go outside and it's snowing. That's a big surprise, right? And as you come to give something, approaches giving it 0 probability, your surprise might even just sort of blow up, you go off to infinity. Maybe you could be sort of infinitely surprised to learn that something you thought was literally impossible is actually the case. The function, it seems sort of right, kind of captures something about how probabilities relate to how surprised you are. And it turns out this function, the thing I'm graphing here, is actually, it's the negative log probability that we assign to the true label. If you don't like thinking in terms of negative log probabilities, just think in terms of surprise. Some kind of way of computing a function that takes a probability and computes how surprised you are by learning that that is the case. But if you want the underlying math, that's actually what it looks like. And we tend in machine learning to call this also the cross-entropy loss. Really just means how surprised are you by the true label, given the probability that you assigned to that label. So if you're very confident that a berry is safe, and the berry is indeed safe, you're not at all surprised. If you're very confident that it's safe, and it turns out that in fact it's poisonous, you're very, very surprised in a very bad way. All right. So here's a function. All I need to know is the probability that was assigned to the true label. The probability that was assigned to this being a 9. Okay? If I give that a very high probability, I'm not at all surprised. If instead I think, no, this is definitely a 7, really low probability it's a 9, and then you tell me it's a 9, like what? I'm very surprised. Turns out that this is the loss function that we want to minimize when we're doing a categorization task. What we want to do is just look at what the correct label was and look at the probability that was assigned by the model to that input example belonging to that category. And then we just compute the log of that and multiply by -1. And it turns out mathematically this gives us this nice function here that we can now descend on, right? Because what we really want to do, notice here that if you're making really good predictions, assigning very high probabilities to the thing that is actually true of the example, then you have a very low loss, right? This function is minimized when you assign very, very high probability to the true label. Okay? I just want to go back to the berries example, right? So safe, poisonous, only 2 possibilities, so it's a little easier to graph than the handwritten digits. Let's go back to that with this in mind, okay? So remind ourselves, right? These 2 are poison, these 2 are safe, right? With just a pretty small model, as long as there's a nice little nonlinearity in there, we can learn to a model that categorizes the berries correctly into poisonous versus safe. Okay? And we saw last time that after we apply this soft max function that we talked about, we're able to have as our input, as a function of the color and the size of the berry, kind of predictions that look like this. In this region, we're predicted very low probability of being safe, and that's good because these ones down here are poison. And up here, where the safe berries live, in this region of the color and the space plane, we're assigning a high probability to it being safe. Okay? Here was our bad model, our bad linear model, right? We couldn't do any better than this with a linear model, but it was pretty bad. Low probability of being safe for these poisonous berries, that's pretty good. High probability of being safe for these safe berries, so that's good. But here's a big surprise, right? We're assigning very high probability to being safe, but in fact, these berries are not safe. Very big surprise, big loss. This is sort of quantificationally a way of seeing what goes wrong with this model. It's got a big loss. We can't do better than it given its mathematics, but we're unfortunately very surprised in a very bad way here. Okay. Here's the better model. What I want to show you is how this surface evolves over the course of training. Okay, so in a moment when I click it, where it's going to start out is what this surface, this probability surface, started out as with its random initialization. And then you'll see it evolve over, as the epochs are going by, it evolves to something that minimizes the surprise, right? Where the surprise is something we can literally see here. It's that gap between the surface and where something actually resides in this space. So let's take a look what that looks like. This is training. This is real model training in action. And there, it's doing pretty well. It's coming. It's going to restart probably in a minute. So as the epochs go by, so it restarted there, right? So as the epochs go by, we're making, what's happening, what's changing this surface is each of these little weights and bias terms are being updated at each step, right? And this is showing the effect. I can't actually show you directly the weights and biases. I don't have the dimensions for that. I'm a poor 3-dimensional creature like you all, but what we can see is how this surface that assigns probabilities to being safe or poisonous, how it evolves over time as these weights and biases are tuned so as to minimize the surprise, right? So as to minimize the gap between where that surface is and where the correct answers actually are. We see that since it was able to learn this function successfully, what we end up with is something that actually does a pretty good job here. All right, so what I'm going to end with is saying something about modern AI text generation. But before I go to that, let me see if there are questions on what we've covered so far.
Yeah, I just wonder if you end up with a situation where all the nines are correctly classified as nines, or with high probability of being nines, you lose some useful information, which is that some nines are good nines and some nines are bad nines. Is that okay, or do we not ever want, especially for large language models, they must want to hold some of that information, but it seems like that gets lost.
It's a great question. That's a really, really good question. What I would say is we probably won't really end up losing that information for the most part, because even though we're pushing the model to learn what are good examples and what aren't, If genuinely in the data a particular 9 is very much an outlier, let's say, relative to other 9s, it's probably not going to assign that high of a probability. And I don't know if you remember it, but there was, I think when I showed you even the trained model, there was some, you know what, I think it was like a 5 that was sort of written like that or something like that. And I think it did correctly classify as a 5, but it gave it maybe 70% probability or something like that. That was at the end of the training. Yeah, exactly. And I think, you know, it's the kind of thing where you look at it, you say, you know, I would also be uncertain about that example. I think I'd go with 5. Apparently it is indeed a 5. But, you know, I'd be kind of unsure about that, at least not absent other information. So it will actually, in general, end up, at least a very well-trained model, will be able to incorporate that kind of uncertainty if indeed the input is such that there is genuine uncertainty about the outcome. Now, I'm not going to say that you can't get models that are overconfident or that because you absolutely can, right? But at least in the sort of the ideal outcome would not necessarily be super high confidence for everything, even though I agree that is what the training objective is pushing towards, but you're actually going to usually have some amount of sort of residual uncertainty. And in fact, it can be a hallmark, this has come up like a hallmark of overfitting can be being overly confident about the training examples, especially ones that are maybe a little more ambiguous. That could be an indication that the model has more memorized its training examples versus extracted information that's generalizable and applicable more generally.
Yeah.
Just to follow, and that would it then be true that this all would be sort of the case insofar as our calling something a bad 9 is saying that it is unlike all the other 9s in a way? Like.
Yeah, I mean, I think that's kind of what we mean by it, right? Or something, or at least at a high level, we say it's a bad 9. It's sort of like a 9 that is not immediately obvious to me that it is a 9, something like that, right? Which, whatever exactly that's based on, my, I guess, vast, at this point, human experience with the number 9, right? Yeah.
Whereas if you want to penalize people who like write the annoying little bar in a 7, you know, then you would have to be specific.
Yeah.
Anything happened between epoch? So no, nothing happened.
No, nothing happens training-wise between epochs. Something that is often a good practice to do is to have a set of data that's called the validation set, which you do not take any gradient steps on, but at the end of a given epoch, you can make predictions about and evaluate your accuracy on. So that's a little bit of a kind of immediate check-in about how well you're doing with examples that you are not taking gradient steps on. So sometimes you would, or often you might include that, but that's not going to be part of the training process per se because you specifically don't take gradient steps on that. Otherwise, you just pick up your weights and biases exactly as they are and start your next epoch with them. All right, so let's talk about text generation. Let's talk about training text generation models. So here's the fundamental idea. The fundamental idea behind training large language models is we can actually treat text generation as a classification problem. Okay, so classification, just like classifying handwritten digits, we can actually treat text generation fundamentally as classification. How do we do that? So let's suppose that we've taken some sentence, human-generated text, something from the internet. Let's just say it was like, the movie was long but worthwhile. Here's how I'm going to go about training my language model. I'm going to use this sentence as both input and label. And this is kind of the fabulous insight. So one step, my input's going to be the word the, because that was the first word that a human put in this sentence, let's just say. Here I will say in this section I'm going to simplify in some ways. I will take responsibility for that. Otherwise we'd be here for a couple of weeks. So the is going to be my input. And what I'm going to use as the label here is the next word that the human who produced this sentence actually chose to use. In this case, movie. And then what I'm going to do is I'm going to take this word the. I'm going to come up with a way of representing it as a series of numbers. This is really going to be something I'm going to train the model to do. Okay? Basically, what you can think about it is I'm going to have a big matrix that is, like a big square of numbers. I'm going to say that each word gets its own row in this matrix. And I'm going to first populate this matrix with random numbers. But I'm going to include this matrix as part of what gets trained. It's going to be the initial input into this thing called a transformer. Transformers are the T in GPT, generative pre-trained transformer. It's an architecture. It's fundamentally a neural network architecture, which means that just as we've seen thus far, in fact, everything that goes on in a transformer is really fundamentally a matter of taking pairs of numbers, multiplying them together, adding them up, with the occasional nonlinearity, which is typically actually going to be in the form of softmax, something that we've seen before. It's not as straightforward as with the kind of standard dense, they're called neural nets, that we've talked about thus far, where every weighted sum depends on every different input. There is a lot more nuance to transformers. Only some things get combined with some other things. There's complexity there. That would take another, hour and a half, 2 hours session to walk through. So I'm not going to walk through that detail for a transformer here. But what I do want to note is that if you understand what a weighted sum is, if you understand that fundamental concept of having two numbers, one of which depends really, it sort of comes from the input, and the other of which is something that is learned via backpropagation, learned via gradient descent, multiplying those two numbers together, and then taking other pairs of numbers like that other pair, adding those all up. If you understand that, you actually understand everything that is the beating heart of a transformer. There's some complications around that, but that is what it is. It is fundamentally these linear operations with some interspersing of nonlinearities, such as softmax. Okay? It may seem implausible, but it is true. But it actually suffices to produce text at the level of quality that you see in commercial AI applications. Okay, so a lot of stuff is going on. It's not a black box, but it's a blue box. It's a transformer. What comes out of the transformer after it's done its bit is another vector. So just another string of numbers associated to this particular input word. Then that vector of number, like set of z values, right? This is kind of like the thing that we fed into a softmax layer to predict which of 10 possible digits something could be. We take this vector, it looks like it's only got 3 numbers, but in fact it would be much larger, thousands in a typical transformer, and feed it into a softmax layer, right? So we're just going to take this and transform it into a probability distribution. A probability distribution over the entire vocabulary of the language, okay, which we have in some way or other delineated at the outset. There are clever ways of doing that end up not sort of limiting the transformer. This would be a very, very large number of categories, very, very large, right? Think of all the words you can think of, right? And some sort of efficiencies there, but really it's a very, very large set of possibilities. We take this vector and we transform it into something that gives us a probability distribution over the vocabulary. So if I haven't trained my transformer yet, if this is the beginning of training, I have random weights and biases in this, in this blue box, right? I get some probability over what I'm going to call, every possible vocabulary word. How do I train it? Train it by treating the true label as the word that the human actually next produced. So I output probabilities, and then I look to see what was actually the correct, and obviously I'm putting this in quotations here, the correct answer, which I'm just going to define as whatever word this human on this occasion next produced. And I look then at the true answer, which is movie, and I say, okay, Let me go back through my transformer, maybe literally billions of parameters, but that doesn't matter. It's a mechanical process. And I say, how can I tune each and every one of these weights and biases so that I will make a better prediction the next time? That is, I will assign a higher probability to this word movie as being the word that comes next. And I really flag, you're not misunderstanding it. And for a handwritten digit thing, you can get like 98% performance. Obviously, you can't get anywhere near, I mean, accuracy doesn't even have so much purchase here, right? Because there are so many sensible words that can come after the, but there are also a lot of words that can't come after the, right? There's just a lot of the, you can't really do that, right? A lot of words that can't come after the. And as we start filling in the sentences, the possibilities narrow. And as we noted at the beginning of the session yesterday, you as humans, you may not be able to perfectly predict the next word that I'm going to utter. You may not be able to perfectly predict that, but you actually have a really strong internalized sense of what are reasonable next words, right? Some things are just bad candidates, and some things are really quite good candidates. You actually have these highly non-trivial probability distributions in your heads as humans, as users of language. Can we use this technique to train a model to internalize that same kind of distribution? And it turns out, amazingly, miraculously, the answer to that is yes. Okay? So here's, right, so there's one input with one prediction. I can use that to train. Then what I'm going to do, I'm going to come down here and I'm going to take now as my input, not that first word, but these first two words. And I'm going to say that the true label, for in this case, for this particular example, the true label, as it were, for the input, the movie, is the word was. Okay? So I feed both of these in, and in a transformer, this one gets to inform that one. Basically, they're the numbers that occur here end up being combined via these weighted sums with numbers that are here. That's really just all that it means by inform. There's nothing, really nothing outside of these kinds of operations. Nothing magic here. Okay? Get some kind of vector out, which I then feed into this softmax layer. Get a probability distribution, again, over every possible word in the vocabulary as I have defined it. And then I look to see what, in fact, was the correct answer. It was. And I use that, again, to adjust these weights and biases. And so I continue my process. Now, the input is the movie was. And now the label, as I'm defining it, is long. Same process, right? Get some kind of vector, feed it in. Probabilities out, train on that. Train on that so that next time there's higher probability assigned to long, less probability assigned to everything else. Keep on going with this, right? But is the next one, right? But, and then here we have worthwhile. Train on that. And I don't do that for just like one sentence or 60,000 sentences or even like 1 million. Even a fairly small model will be trained on 1 trillion or more words, right, in sentences, tokens, right? Vast quantities of data. So basically, this kind of approach, if you have small data, this kind of approach is terrible. It doesn't go anywhere. It doesn't do anything. The signal isn't there. But it turns out that at scale, if we have access to unimaginably vast quantities of language produced by expert users, that's all of us, namely the internet, that this is actually sufficient. If you use that vast quantity of text as your training corpus, is sufficient to train a model via this kind of approach to produce very sensible, very helpful, very apt language. The model is able to extract from the signal contained in this vast data set, just simply by being trained to predict what the next word is likely to be, it's able to train a model that is able to do the sorts of things that we see in AI today. Let me finish by just showing you what actually happens when we're generating responses in chats, right? So that's the training process, where we have text that we treat as both input and label, right? So the text is both what the input is and also what we're considering the true label to be. What happens when the machine is generating responses in a chat? Well, so suppose you're chatting with ChatGPT or what have you, and suppose your input is, tell me about AI, right? Perfectly reasonable thing. What's going to happen is that this is the starting input to the language model, okay? So each of these get transformed, get mapped to their row, if you like, in this very, very large matrix, fed into the transformer, lots of weighted sums being computed here. We get out some kind of vector here, and we feed it into this softmax layer that has the outputs, if the model is well trained, a very good probability distribution over the entire vocabulary of the language. We then select from that a high probability word, and that is the output. So maybe the machine begins by producing the word artificial, okay? And then it takes its own output, appends it to your prompt, runs the whole thing through again. And now it predicts what the next word should be given the prompt and that first word. So probably here the next word is going to be intelligence, right? Take all of that, run it back through. Maybe you get is as the next word, and so on and so forth. You know, artificial intelligence is a technology that's transforming the world, right? Whatever, in fact, that sequence is, this is the fundamental generation process. And that training schema that I showed you before, it turns out it is able to produce models that are able to give outputs that are sensible and helpful. If it's really hard to see how multiplying pairs of numbers together, where one of those pairs was just simply adjusted via pretty simple calculus operations to be bigger or smaller so as to improve the predictions the next time. If it's hard to see how all of that can conspire to give the kinds of language models we now have access to too, that doesn't mean you're missing something. I think it means you're following the plot. What I'm saying is true and accurate, but it's also, I think, one of the wonders of the modern era that these simple operations suffice to do this. I think it's an incredible thing. And all right, I think we're out of time, but if anyone has any questions, you can come up and ask me at the end. Thank you all so much.